Okay, YouTube, in this module of videos, we've been focusing on solving systems of linear equations that have one solution. And in these videos, this one and the next one, we're going to focus on systems that have no solutions or infinitely many solutions. And so we've seen that certainly, when we're looking for the solution to a system of equations, we're looking for any points x, y that satisfy all the equations in the system. And so one thing that we've talked about is, graphically speaking then, if these are the solutions, each line represents the set of solutions to each of the equations, then the solution to a system would be any points of intersection. And so the three different possibilities we're going to look at here are essentially these. We would say that, either our system has one solution, and that solution is right there where these two lines intersect, or these two lines may be parallel and therefore share no common x's and y's simultaneously. Okay. Likewise, we would say that infinitely many solutions might be a case where, and this is kind of hard to see here, but these are two lines that overlap at every single point x and y on both of their equations. And so you could see that any point on either of those equations would, when you plug them back into their own equation there, make them true. And so they're all solutions. And so we're going to look at the no solution, infinitely many solution case. But exactly, what we want to look at here, we say that the number of solutions to a system of two linear equations and two variables is given by this table right here. So we either have one, none, or infinitely many. Now, one thing that I would like to comment on, and this is a matter of vocabulary before we move on, is that we often give these systems names. And so you'll notice down here this little text box, it says a linear system with no solutions is called an inconsistent system. And it says if you attempt to solve such a system by substitution or addition, you will eliminate both variables, but a false statement such as 0 equals 12 will be the result. So we say it doesn't equal 12 because 0 isn't 12, but essentially, we would see that if it's inconsistent, we end up with no solution. So we would say that the no solution case, we're going to give this a name. We refer to this as an inconsistent system. Now, this is something we'll continue to talk about in the future, but I want to introduce it now. We would say that if a system that has no solutions is inconsistent, then what should we refer to a system that has at least a solution as? And I suppose we would refer to these two systems here as consistent systems. So when you hear the word consistent system, okay, I want you to know that that means you have at least one solution. Okay, so now one thing that we're going to do to distinguish between these two cases is essentially say that if these two systems, okay, have at least one solution, but one has infinitely many and one has just a set number, then we're going to say the one that has just a set number is going to be considered to be an independent system. And I always think about this as kind of like these two graphs don't live with one another. They kind of do their own thing. It's just that they're independent of one another except for at this one point. Whereas these two graphs right here completely live with one another. They're on top of one another. They have the same solution sets always. And so we will refer to that as a consistent dependent versus a consistent independent. So let's take a look in this video here at some inconsistent systems and this idea that you'll end up with a false statement. So looking at this first system here, it says that we want to solve it. You'll notice that it doesn't say which method we have to use in order to solve this. And so, one thing that I might try, just as a real quick exercise and doing this, is representing these graphically. And so we would say that looking at these, they're both in standard form. So perhaps what we'll do is we'll go ahead and graph them by using their intercepts. Okay. So to find the x and y intercepts here on our first line, if we plug in 0 for x, okay, we get 6y equals 12, or in other words, y would have to be equal to 2. And if we were to plug in 0 for y, okay, 0 for y, we get 4x equals 12, or in other words, x would have to be 3. And so to graph this equation right here, we say 0, 2. I mean, it would look like this. We say 0, 2 would be our y-intercept, and 3, 0 would be our x-intercept. Essentially, here are all the solutions to this very first equation right here, and I'm really keen on labeling this. We say 4x plus 6y is 12. Now to look at this other equation, 6x plus 9y is 12. If we were to look at its intercept, 0 for x would mean that 9y equals 12. In other words, we get y equals 12 ninths, which is the same thing. Let's see, 12 ninths, common factor of 3 would mean this is 4 thirds. I'm going to say 1.33 repeating. And then down here we would say, well, then the x-intercept here, if we look at the x-intercept, x is 2. So we would say 2. So to graph this, we would say, well, 2 zeros about right here. 1 1/3 is about right here. The interesting thing is, if I were to graph these, and I know you wouldn't probably graph them this accurately, but I know what's up with these two lines. Matter of fact, we're talking about inconsistent systems. So we could see that graphically, if we had a calculator, we could have done this. Desmos, we could have done this. But graphically, we already are going to support the case that this system has no solutions. And so we're going to say that this is an inconsistent system. Inconsistent. But here's what we're going to do now. we are going to look at this not graphically, but also algebraically. So algebraically speaking, with a system that has non-one coefficients, like this system has here, I'm going to opt to use the addition method, which is really just kind of the more common method anyways. But it looks like I'll have an easier time maybe eliminating my x variables here. And so it looks like we're going to have to multiply both equations. But I want my x coefficients here to be opposite. So I say, what if I multiply this by maybe even smaller? We could make them both 12. So if I take -4 times a -3 and maybe a 6 times a 2, something like this here, then rewriting our system, we would get -12x, okay, we're just distributing on the top here. We would get -12x minus 18y's equals -36. And for our second equation, distributing throughout here, we would say 12x, positive 12x, plus 18y's gives us a positive 24. So something interesting happens here, and I hope you see it. We get all of our variables to cancel out. And so people often ask, like, what do you write there? You know, I know it's -12 on the right, but what do you write on the left? You just write 0. You say there's nothing left on the left-hand side. But something like this right here, essentially that this is an invalid statement. This is not a truth. And so because this is invalid, we would say that this solution or the system has no solutions. But graphically speaking, you know, also what we want to recognize is that they must have, if you're talking about linear systems, parallel lines. If they're both lines, they must be parallel. And so with linear systems, we're going to see parallel lines imply that we have no solutions and that we end up with this 0, always our variables canceling out to 0, equaling something that is not 0. So what I want you to try here is that go ahead and try to solve this system here. I'd encourage you to graph it as well as solve it by addition, really, and then see that you get no solutions on this. Cheers.